Now, when we're talking energy and we're talking metabolism, each of those steps in those metabolic pathways is going to take some energy to take that next step. Remember, with each step, your substrate, your reactants, however you want to think about them, has to go through some changes. To get that energy, it's going to have to come from somewhere. Now, in the chapter, in the textbook, if you read in section 6.2, it discusses this variable known as delta G. Delta G is basically a way of describing how much energy is in a reaction. What we've found, and we'll talk about over the next couple of lectures, is that the higher the delta G, the more positive it is, well, the less likely a reaction is to occur, because it's going to take energy from outside to be pumped into it. Think upstairs in chemistry. When you put two compounds, two chemicals, two reactants into a test tube, and then you had to hold it over the Bunsen burner. Okay? The Bunsen burner is supplying thermal energy. It's going to make the molecules and those reactants vibrate more and faster. Whereas other reactions, you just had to put it in the test tube, and then they said, be careful, it's going to get hot, and it just heats up on its own. Well, it turns out those are reactions that are delta G is below zero. It's negative. Those are reactions that are just going to occur, and it's going to give off energy. What does that mean here for biology? Well, if you look up here at this figure from the textbook, at this figure from the textbook, what you'll see is that the purple line here represents how much energy is involved in one of those metabolic steps, one of those reactions. The reactants, within the reactants, there's a set amount of energy that's there. But there's not much going on between them. Some more energy has to be placed into them to get them more vibrating, get them moving, blah, 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 so that they come together and then they split and give you two new products or one new product, whatever. That amount of energy that had to be put into the system is right here. As it goes up, 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 more energy is put into the system, into the reaction, into the mix, and then boom, the reaction will occur. We see that the reactants, just because of what they are, will have a set amount of energy involved in them. That's where it says the delta G. There's so much energy there, but there has to be more added in. You'll notice just below the purple line is that little green line that still has a bit of a hump, but it's a much smaller hump. What we're going to see in the next lecture is that this coincides with the work of enzymes. Enzymes acting as catalyzers. Now, catalyzers, you've seen those upstairs in chemistry. We're going to use that again. Chemistry, put two reactants into a test tube, and then you had to put in something else, a metal or something like that, that's going to help spark the reaction. That's a catalyst. Well, turns out we in biology also have catalysts. But here our catalysts are proteins. proteins known as enzymes. Under normal conditions, all the reactions in your body will happen on their own. It's just going to take some time. Because the source of the energy to get that curve to go up, 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 up to the peak of the purple and then down to products, well, that accumulation of energy is from heat. 37 degrees Celsius, 98.6 degrees Fahrenheit. You produce some heat. And it's just going to take time for that thermal energy to build up, to get those molecules vibrating faster and faster, so they actually will start bumping into each other. Reactants can become products. That's what it means when you look over the second bullet. Heat helps reactants reach their transition state. The transition state is at the peak of that energy, that purple. When it hits there, the reactants are vibrating. The reactants are at the point where things can be changed. Now, as I said, some reactions take energy to get them to happen. Some reactions will give off energy. If it gives off energy, energy is released. We refer to these as spontaneous. These are going to be, as I said, as you look to the far left, delta G less than 0. How do you calculate delta G? Delta G is a calculation based on temperature, based on how much energy is already present in the chemical bonds, based on how much is going to be lost. Don't worry, I'm not going to ask you to calculate delta G's. But when you look at it, delta G less than 0 means the reactants are going to come together. They're going to react together and become products. The products, in that going from reactants to products, that reaction is going to give off energy. Later in chapters, we're going to discuss how this giving off of energy is going to power the endergonic reactions. The endergonic reactions takes reactants that have a very low energy state, pours energy into them, gets them excited so that they can form products that have a lot of potential energy in the chemical bonds.